Hi everyone. In today's introductory topic, we're going to focus on exponential functions. Functions that can be expressed in the form y equals a to the power x, where a is neither 1 and positive, are called exponential functions. A is called the base of the exponential function and determines its behavior. Graphically, when the value of x increases by 1, the y value will change by a multiple of a. This means that the exponential functions increase when a is greater than 1. For example, y equals 4 to the power x is an exponential function with a base a equals 4. Every increase of 1 unit in the x value results in y becoming 4 times larger. It also means that exponential functions decrease when a is between 0 and 1. For example, here is a depiction of y equals 1/3 to the power x. It's an exponential function with a base of a equal to 1/3. This time, every 1 unit increase in x results in y becoming 3 times smaller, or if you prefer, 1/3 of the value y had 1 unit previously. In all cases, exponential functions are defined over all real numbers, and they remain positive. In other words, the domain of an exponential function consists of all real numbers, and its range is from 0 exclusively to infinity. The horizontal line y equals 0, in other words the x-axis, is a horizontal asymptote of y equals a to the x. Let's rewrite y equals 2 to the power 2x as a basic exponential function, and let's describe its behavior. Here we're going to use properties of exponents to rewrite 2 to the power 2x. Now, 2 to the power 2x can be seen as 2 to the power 2 all to the power x because of rules for consecutive exponents. In other words, 4 to the power x. Therefore, y equals 2 to the power 2x is identical to y equal 4x, 4 to the power x. This is an increasing exponential function where y grows by a multiple of 4 whenever x increases by 1. In fact, it's the graph that we drew a little bit earlier. Let's rewrite y equals 9 to the power minus 1/2 x as a basic exponential function and describe its behavior. Once again, we're going to use properties of exponents. 9 to the power minus 1/2 of x is equal to 9 to the power minus 1/2 all to the power x. Consecutive exponents multiply, but we can just as well separate them. Now remember that negative exponents means that we can flip the number to the denominator, and that's what we've done in the next step. 9 to the minus 1/2 is equivalent to 1/9 to the power 1/2. Now a fractional exponent, such as a half, is equivalent to rooting, so the root of 9 is 3. In other words, y equals 9 to the minus 1/2 x is identical to y equals 1/3 of x. This is a decreasing exponential function where y decreases to 1/3 of its value whenever x increases by 1 unit. And this is the other function that we drew a little bit earlier. A base that is frequently used both in science and in finance is called the natural base e, which is Euler's number. E is roughly 2.718. Just like all other exponential functions, the base determines the behavior of the exponential function with base e. The y value grows by a factor of e whenever the value of x increases by 1 unit. And here is a sketch of that graph. Notice how the curve goes through coordinate point 0, 1, and when x is 1, so one step further, the height has now become roughly 2.7. So that's how the e has affected the height of the curve for every step forward. As every other function, an exponential function can undergo transformations. That could mean horizontal or vertical translations, could mean reflections, could mean horizontal or vertical compressions or stretches. For example, f of x equals 2 to the minus x plus 1 minus 3 can be graphed by applying transformations to a similar exponential function that we'll note in a second. Now, minus x plus 1 can also be written minus parentheses x minus 1. So a little bit of rewriting here allows us maybe to make a connection. The function as it's currently given is obtained from the basic form 2 to the power x, but a few things have occurred along the way. First of all, there's a reflection across the y-axis due to the minus 1 factor in front of the x minus 1. So in blue, you have the basic curve y equals 2 to the power x, and in orange, you would have its reflection. Secondly, the curve can be shifted 1 unit to the right due to the x minus 1 form. In this case, h is 1, and recall that it causes a 1 unit shift to the right. Notice how the orange curve has been shifted by 1 unit relative to where it was a few moments ago. Finally, a vertical shift of 3 units downwards can be applied due to the added constant minus 3, which is a k value. And there we go, our curve is shifted 3 units down. This time, rather than having y equals 0 as a horizontal asymptote, the curve in orange would have y equals minus 3 as a horizontal asymptote. Note that algebraic manipulations would also allow us to write f of x equals 2 to the minus x plus 1 minus 3 as follows. Now remember, added exponents means we could actually see this as common base exponents involved in a product. So 2 to the minus x times 2 to the 1 would be identical to 2 to the minus x plus 1. 2 to the 1 is 2 and can be brought anywhere to the front. 2 to the minus x is equivalent to 2 to the minus 1 to the x, which in turn is a half to the x. So this time the comparison is a little bit different, but we could certainly think of this function f of x as being obtained from the basic exponential y equals 1/2 x, but through a few transformations, the first of which is a vertical stretch due to the fact that the factor of 2 is multiplying 1/2 of x, 1/2 to the x. A vertical shift of 3 units downwards also occurs due to the added constant minus 3, which is a k value. So here is the basic function, or the basic exponential, 1/2 to the power x. Multiplying by 2 creates a vertical stretch. Notice how it is stretched upwards. Every value of y is doubled. And finally, the minus 3 shifts everything downwards. And this orange curve is identical to the one we found earlier through different ways of seeing the operations.